Could you hear us?
Yeah, thank you so much, Mike. Can you hear me okay? I'm on Jacob
Perfect.
Stubbs' computer.
Yeah, it's perfectly well.
All right, awesome. Well, thank you, Jacob, for loaning your computer. The platform crashed mine. So I'm going to talk a little bit about the where. Next slide, please. So the question we're all interested in is how do we identify a therapeutic target for addiction? And this is just one component. As Hamed gave in his brilliant introduction, I'm just focusing on the where, but need people like Colleen and Hamed to tell me more about the how. But focusing on the where, there's a lot of different approaches to this. Next slide. One of the most common approaches is neuroimaging of symptomatic patients. Makes a lot of sense. If you want a therapeutic target for something like addiction, find a bunch of patients with addiction, scan them, and look for neuroimaging correlates of addiction that you might be able to target with something like TMS. Next slide. But there's a problem with that approach, which is no matter how large you increase your cohort size or how much you improve the strength of your scanner, in the end, neuroimaging is usually looking at correlates of the symptoms we want to treat, not the causes of the symptoms we want to treat. Next slide. So a slightly complementary approach, or a different approach that we've taken in my lab, is to look at causal sources of information that may give us insight into our therapeutic targets for neuromodulation. And there's really a finite number of causal sources of information for mapping out symptoms. And we're going to focus today on one of the most common sources of causal information and the most traditional, which is focal brain lesions. Next slide. So this is how, yeah, there you go. This is how lesion-based localization is supposed to work. You take 3 patients that all had focal brain damage that resulted in a similar behavioral effect. Usually a new symptom, but it could also be improvement in a symptom. And you take those different patients with focal brain damage, you map out the location of brain damage in each of these patients, and you ask, where do these locations of brain injury that cause the same symptom or the same behavior, where do they intersect? And if you get an intersection between those lesion locations, that gives you a very strong causal inference that that specific location in the brain is playing a causal role in that symptom or behavior. Next slide. However, when we actually use this lesion-based approach, this is what happens. More often than not, you take the location of brain damage in different patients, map it onto a common atlas, and you find out that these lesions that all caused a similar behavior, they don't line up. They don't intersect one brain region. Next slide. And that's when we turn to a resource called the Human Brain Connectome. This is a wiring diagram of the human brain that's been built as a collaboration in the neuroimaging community over the last few decades. And we have anatomical wiring diagrams. We also have functional wiring diagrams. And I'm going to focus today on the functional wiring diagram. This is based on spontaneous fluctuations in the fMRI signal. And they tend to be correlated between anatomically connected regions or even polysynaptically connected regions. Next slide. So when we turn to our problem of lesion-based localization, we can now use the wiring diagram to ask a different question. Rather than assume that lesions that cause the same behavior intersect one brain region, we can ask whether those lesions intersect one connected brain circuit. Next slide. And this approach to mapping out lesions that cause a certain symptom behavior has been very useful across a wide variety of different neurological or psychiatric conditions. And it's a technique we call lesion network mapping. Next slide. So before I jump into addiction, I'm going to give you another example that gave us the motivation to use this approach to go after addiction. Next slide. These are 11 patients that had bad essential tremor, that had focal brain damage, and their essential tremor got better. So these 11 cases have to be telling us something very important about where our therapeutic target for tremor must lie. But when you look at these 11 cases, they're all in different locations. Which one of these 11 cases do you want your surgeon to emulate to fix essential tremor in other patients? Next slide. But when we turn to the human connectome, we can ask, what are all 11 cases connected to? And in fact, which connections are specific to these 11 cases that got rid of tremor compared to any random stroke that a patient might have? And we see that all of these cases were all connected to a very specific location in the thalamus. Next slide. And that was exciting to us because that's exactly the spot in the brain where we implant our deep brain stimulation electrodes to make essential tremor better. And this gives us the precedent that says, hey, we might be able to take lesions in lots of different locations that lead to symptomatic improvement filter those lesion locations through the connectome and identify an effective therapeutic target for that disorder, that symptom. Next slide. So now what we're going to do is use that same approach to go after lesions that led to remission of addiction. Next slide. And this is actually a huge collaborative effort across a lot of different labs, a lot of different experts in brain imaging and addiction. And it actually had 3 co-first authors on the paper, Juho Jucha, Khalid Moussaoui, and Sean Siddiqui, that deserve full credit for leading this team and this research. Next slide. So what Juho did is he looked at lesions that got rid of addiction. And this is actually a long story that goes all the way back to the 90s, where they published a series of patients that had focal damage to the insula, and those patients had relief of smoking addiction. And I don't mean they just quit smoking, they lost their addiction. No sense of craving, no relapse, no withdrawal symptoms. And they were able to show that lesions that hit the insula were a little bit more likely to lead to relief of addiction and remission of addiction than lesions elsewhere in the brain. Next slide. However, when you actually look at these data sets, most of the lesions that led to addiction and remission weren't in the insula. And in fact, most of the lesions that hit the insula didn't lead to addiction remission. So there had to be some other element here. Just lesion location alone wasn't explaining it. And in fact, as people sought to replicate these findings, they were getting heterogeneous results. Next slide. So Juho put together all the data sets we could get our hands on of lesions that either led to remission of smoking addiction or lesions that did not lead to remission of addiction. In fact, these patients kept on smoking. So every one of these patients was a cigarette smoker. Everybody had a stroke. Some people lost their addiction, other people didn't. And the first thing he did is just say, is there any single spot in the brain that when lesioned leads to loss of addiction? And he came up with a giant goose egg. There was no single spot in the brain, including spots in the insula, that when lesioned were significantly more likely to lead to loss of addiction than compared to non-quitting lesions. Next slide. But when Juho turned each one of these lesions into a network and said, show me the set of brain regions that each lesion location is connected to, and then said, are there any connections significantly associated with loss of addiction, then he got significant findings. Next slide. What he found is that lesions associated with loss of addiction were connected to a very specific network of brain regions. So they were connected to the insula, but also other regions like the dorsolateral prefrontal cortex and the anterior cingulate. They were also negatively connected to other sets of regions. And when you drop the threshold, you actually saw a lot of very interesting topography that fit a lot of findings from the addiction imaging literature or even animal models of addiction. So striking dissociations between the ventral and dorsal striatum, striking dissociations in the frontal cortex. Next slide. Juho then wanted to know, is this a circuit for just relief of smoking addiction, or could this generalize? Now, we did not have a data set of people with alcoholism that had a stroke that lost their alcoholism, but we did have a data set of patients with focal brain damage where they then queried their alcoholism risk using a validated alcoholism risk scale. So you could look at the connections associated with reduced risk of alcoholism based on this assay and ask whether that network looks similar to the network for lesions that got rid of nicotine addiction. And they looked very, very similar. And in fact, this was highly specific to reduced alcoholism risk compared to 17 other neuropsychological variables that we had in that same data set. So we thought that this might generalize to addiction, not just be specific to nicotine. Next slide. What we then did is we said, okay, we have a set of connections that are significantly associated with loss of addiction. So we went back to the connectome and we said, all right, what voxels in the brain best match the connectivity profile of a lesion that got rid of addiction? And can we refine our therapeutic targets? So we think one of our therapeutic targets is the insula. What spots in and around the insula have exactly the right connectivity profile for a lesion that gets rid of addiction? And what we found is that it's specifically the anterior insula. In fact, it's actually in the frontal operculum. That'd be the one spot in the brain where if you put a lesion right there, that would have the ideal connectivity profile to get rid of addiction. There was also a second spot adjacent to the anterior cingulate. Again, the anterior cingulate is a traditional lesion target for addiction. People have run human studies lesioning the anterior cingulate to try and get rid of addiction. But our data suggests that they were close, but not exactly where we would predict is the ideal target. In fact, our peak spot where you'd want a lesion to get rid of addiction was actually in the paracingulate gyrus, just dorsal to the anterior cingulate. Next slide. We also looked at where in the brain has exactly the opposite connectivity profile of a lesion that gets rid of addiction. And you can hypothesize that that might be the ideal target for excitatory brain stimulation. And what we found is in red there in the middle of your screen, the ideal spot for quote unquote excitatory stimulation was in the frontal polar cortex. And we were actually really disappointed when we got that finding because we said, oh, well, that doesn't line up with, you know, the big FDA approved, BrainsWay TMS coils that have been approved for addiction. And there's an FDA approval for this H4 coil for smoking addiction. It was designed to target the dorsolateral prefrontal cortex and the insula. However, when we actually looked at the electric field model generously given to us by BrainsWay, what we found is that the peak electric field intensity was actually not in the dorsolateral prefrontal cortex or in the insula. It was in the frontal polar cortex, lining up exactly where our data suggest excitatory brain stimulation for addiction should be targeted. And shortly after that, they came out with new data for a totally different TMS coil, suggesting some value in alcoholism. Now, in between their smoking trial and their alcoholism trial, they actually switched up their coil, and it's got a very different electric field distribution. However, it also hits this frontal polar cortex. And in fact, almost the only spot in the brain where their smoking coil and their alcoholism coil intersects is exactly where we would predict that excitatory brain stimulation might be effective. Next slide. So 3 take-home points. One is that lesions can provide causal links to human neuroanatomy. Take-home point number 2 is that the human connectome can be used to map these lesion locations onto brain networks. And number 3, lesions that improve symptoms like addiction may be particularly valuable for identifying our therapeutic targets. Again, focused on the where. Next slide. So thank you again to my multidisciplinary team. I can't emphasize enough how much I do not know about addiction and how much we relied on a team approach to brain science to go ahead and perform this study. Next slide. All right, thank you so much for having me.
Thank you very much, Mark. It was a really thought-provoking presentation, and people are really excited about what you have found. And there are lots of discussions within the community how we can use the maps that you generated to inform the next series of trials in the field. And I hope that you will kind of help us in terms of kind of pushing the field forward. And I mean, I'm sure that there are we'll have lots of discussions during the other presentation about this specific kind of series of finds.